Okay, in this video we're going to go through chapter 6 and we'll go through sections 6.1 and 6.2. So 6.1 starts talking about the area of a polygonal region. So it defines the unit square as a unit square is a square whose sides each have a length of 1 unit. So by definition we take its area to be 1 square unit. And we will now examine 3 cases. So I have a little typo there. Okay, so case 1. Take a square that is 3 by 3 and divide it into unit squares, remembering that a unit square is a square whose sides each have a length of 1 unit. So here is our square. So this square is 3 by 3. And I'm dividing it into 9 unit squares. So how come I pick 9? Well, 3 by 3 is 9 squared, and therefore I must have 9 of 1 unit square. So each of these boxes right here are 1 unit square, and I have 9 of them. So in case 1, that's how we're defining area. Okay, let's move on to case 2 in the next slide. Okay, so case 2 moves on to working with rational numbers. So rational numbers are just numbers that can be expressed as ratios. So don't forget the word ratio is in the word rational. So a rational number that's not a whole number, so we're going to say A equals P over Q, where P and Q are 2 relatively prime whole numbers with Q not equal to 0 or 1. So in our example down below, so right here, we are saying that A is 2/3. At this point, you know only a formula for the areas of squares whose whole side lengths are whole numbers. Therefore, you must think of a way to reduce the case 2 to case 1 if we're going to apply the theorem we just learned. If you duplicate the sides q times, as in the following figure, you get q squared squares, each of which is congruent to the original square. Since each side of the resulting large square has a length of p, which is a whole number, it follows from case 1 that the large square's area is p squared, and therefore the whole square's area is p squared over q squared, which is a squared. Okay, so they're just kind of applying what we've learned so far. So you basically know that the area of a rectangle is length times width, no matter how you cut it. Okay, let's go ahead and we'll look very, very briefly at case 3. Okay, so case 3 in our text extends this argument to A as an irrational number, and it is determined that the area of a square is ultimately a squared once more. So we're not going to spend a whole lot of time on this theory. So let's move into section 6.2. So 6.2 addresses the approximate values for the area of an irregular shape. So in this section, our author intends to explain how to approximate the area of an irregular shape using a method called Riemann Sums. And I think this is an important exercise, but I prefer to do this in a slightly different manner. So we're going to use Khan Academy to introduce this method. So what I'd like you to do is to open our PDF of our notes on our web page. And if you could first go through and listen to the introduction to Riemann Sums. So click into here and watch and listen and take notes on this video. Then once you've completed that, I'd like you to go to the next one, and the next one is entitled Over Approximations and Under Approximations Using Riemann Sums. So watch that as well, because I want to talk about how we can practice this method. I think these videos are very, very valuable. So take your time, listen to them. You might want to write the results, or as Sal walks you through the problems, write it down and make sure that you can pause the video and make sense of this. And then you and I and the rest of our class, all 4 of us, well, three of us, I guess, will do some more practice on this. Okay, so here's our first practice. So imagine we've been asked to approximate the area between y equals g of x, so that's the function, and the x-axis. And we're only going to focus our attention from x values of 2 to 6. So 2 to 6 only. Okay, if they ask us to use 4 uniform subdivisions, then we're going to figure out what our delta x is by saying 6, which is the high value, minus 2, which is the low value, divided into these 4 equal sections. So 6 minus 2 is 4. 4 divided by 4 is 1, and therefore our widths will all be 1s. So each of our rectangles, this is key, will have a base with a width of 1. So I'm going to look here, and I'm going to change my color so that it shows up a little bit better. So here is one width right here. Here's another one, and another one. So we should have 4 uniform subdivisions. By uniform subdivisions, it means the width and not the height is uniform. So looking at this, and we are going to do left Riemann sums. So we're starting from 2, so our first subdivision is 2 to 3. Since we're doing left Riemann sums, we're going to go up the left side of this rectangle. Okay, there's rectangle 1. Go to the 4, go up, hit the curve, go horizontally across. That is rectangle number 2. Then go to the 3, go up and hit the curve, and go horizontally across to your left. Whoops. To your left. That is Riemann sum number 3. And then go to 6, go up and hit the curve, and go across, and that's going to be Riemann sum number 4. So we have 4 rectangles. So if we are using, now excuse me, what did I just do? I believe I may have done right Riemann sums. Let me go back and do left Riemann sums. So let's see if I can do that. There we go. Okay, so left Riemann sums, I do apologize. We're going to go up to the curve. So f of 2 is 3, and go across and down. That's our first rectangle. Then go to 3. Left Riemann sum says we hit it from the left side, go across and down. That is our second rectangle. Okay, left Riemann sums for 4. Hit your graph and go across and come down. That's our fourth rectangle. Left Riemann sums for our for our fourth rectangle. That was our third. You go up from 5, you hit the curve and you go across and come on down. Those are our left Riemann sum rectangles. There are 4 of them. They asked us to have 4 uniform subdivisions. We have it. I've given you these values right here, here, and here. We are using the first 4 values when we do the left Riemann sum. So that's here. Changing color. When we do the right Riemann sums, instead of starting at 2, I start at 3 and go up to the 3 and go across and back to the 2. The green rectangle is that first rectangle. Then go to 4, go up and hit the curve, go across and down. That's our second Riemann sum rectangle in green. Go to the 5, go up and across. That is our third Riemann sum rectangle in green. Go to the 6, go up and across, and that ends up being our fourth Riemann sum rectangle in green. So we're going to use not the first one, but the second, third, fourth, okay, so, and fifth. Okay, so those four. We're going to use those when we do right Riemann sums. So see if you can make sense of this when I add all the rectangles. And remember, the length times the width is the area of the rectangles. So I'm going to approximate the area under that curve as an area of 4 rectangles. If I do left Riemann sums, I get an area of 20, and I should change that for a second. I'm going to make that red. Left Riemann sums gives me an area of 20. If I do right Riemann sums, that gives me an area of 21. 2 different approximations. So let's move on now to the next page. Okay, in this next problem, it says approximate the area between y equals h of x and the x-axis from -2 to 4. So from -2 to 4. So the blue shaded in area. And I'm being asked to use a right Riemann sum approximation with 3 equal subdivisions. So to figure out my base, I say my base equals -2 minus 4 over 3 equal subdivisions. So delta x equals -6 over 3. That equals -2, but we really want the absolute value of that. So we're going to go in equal subdivisions of 2. So here's our first, then here's our second, and here is our third. So yes, that will give me 3 subdivisions. So we are asked to use not left this time, but right Riemann sums. So we start out with -2 and 0. Because we're doing right Riemann sums, we're going to go vertically up from 0 to the x-axis, and I hit it at 4. I go across and I come down. Here is my first rectangle. What are those measurements? We're going to come back to it in just a second. Okay, let's find our second rectangle. So that's going to be between 0 and 2. So since we're doing right Riemann sums, go up to the 2 and go across to the 0. Okay, going across to the 0 and then come on back down. Okay, so this is our second, rectangle. I'm going to make this a little bit bigger. There we go. Second rectangle. Our third and last rectangle, it's right Riemann sums to go up to the right of it. And I hit the curve at 4 and I go across, and here we go. That's another area. So you can see that, let me change our color slightly. Let's go to red. Here I'm not approximating, so for that first rectangle it is an underestimate. The second rectangle is an underestimate by just this little bit. And the third rectangle is an underestimate by this little bit. So we are underestimating the area under the curve using this method. But let's see what we can ascertain about this method in just a sec. Okay, let's determine the area of each of those 3 rectangles. So the bases are all 2's. So here are my bases. So the height of the first rectangle is 4. So 2 times 4 is 8. The height of the second rectangle is 6. 2 times 6 is 12. And the height of the third rectangle is back to being 4. And 2 times 4 is 8. So 8 plus 12 is 20, plus 8 more is 28 square units. And that is the area approximated using the right Riemann sums method with an n, which n stands for the number of equal bases for your rectangles and n of 3. So let's move on to the next page. Okay, so on this page it says approximate the area between the x-axis and h of x, and this time they gave us a function. So h of x equals 1 over 7 minus x, and they would like us to figure out the area under that curve, between that curve and the x-axis, between the x values of 2 and 5. And they would like us to use a left Riemann sum with 3 equal subdivisions. So first off, figure out the area of your base of your rectangles and take your range, which is 5, well, I guess that's your domain, 5 minus 2, and I want 3 equal subdivisions. So in that situation, my change in x is going to be 3 over 3, or 1. Alright, so I'm going to do left Riemann sums. So that means I'm going to start up from 2, I'm going to hit that blue axis, or that blue graph, go across and come down. So here is my first rectangle. Then I'm going to continue my left Riemann sums. I'm going to go to the 3, I'm going to go up to the axis and go across to the 4 and come down from the 4. That's my second Riemann sum rectangle. Then go up from the 4, hit your x-axis on the left and go across, and we're going to go back down to 5. So we can see that we are kind of underestimating the area under that curve. Although there is not a whole lot of wiggle room. So what do we need? Well, we need to figure out the area of the base. So it looks to me like each of these bases have an area of 1. So that's 1, 1, 1. So the height equals, for the first rectangle, f of 2. So that's going to be, looks like 1/5. So let me just look at this for a second more and we'll figure this out. If I'm doing, let's say I'm doing left Riemann sums, I'm going to go up to the 2 and then run across. So f of 2 is going to be 1/5. Okay? So my first rectangle is going to have an area. So let's say the area is an approximation of 1 times 1/5. Go to the next area. And the next area, when I start at 3 and I hit that axis, I have 1 over 7 minus 3. So that is 1/4. So 1/4 is going to be 1 times 1/4. I have one more rectangle I need to figure out the area of. If I'm doing left Riemann sums, I'm going to go up. I'm going to hit the axis at 4 and go over. So f of 4 is 1 over 7 minus 4, which is 1/3, and it's 1 times 1/3. So I now have my sum of my rectangles, which is an approximation for the area under the curve. So I have 1/5 plus 1/4 plus 1/3. So to figure out the area, I believe the least common multiple would be 60. So my area is going to be, let's turn the first thing into 60, so it's 12 times 1/5 times 12 over 12, so that's 12 over 60, plus 4 goes into 60 15 times, so 15 over 60, plus 20 over 60, so 20, 35, 47. So that area is 47 over 60 units squared is the area under that curve, using left Riemann sums. So this area is going to be 47 over, over 60. Okay, alright, let's move on to the next page. Okay, at this point we have done left Riemann sums and right Riemann sums. So now we're going to do another version that kind of is an approximation of both, and that version is called Midpoint Riemann Sums. So there is this video right here on Khan Academy which explains it. So I would stop this video, watch that video, and then come back to me again. So our practice, use the midpoint Riemann sums method using 3 equal subdivisions, and you want to run it from 0 to 3. So to figure out what our base is, change of x equals 3 minus 0, and I need 3 equal subdivisions, so that means my base will be 1. There's a base right here. So let's think about this. We're going to go in the middle of it. So go up from the point 5, go over to the right, go over to the left, and come down. That is our first rectangle. So why don't I just change color for every rectangle? So the next one is going to run from 1 to 2 because our delta x is 1. So I'm going to go up in the middle. At 1.5, I'm going to go over to the right and over to the left, and the green rectangle is our second rectangle. Okay, so we have a green one and a red one. So let's get the last one. So well, let's just comment for a second. It looks to me like the red is an over approximation and the green is an under approximation. Alright, so what we're going to do next, well, I take that back about the red. Look at this. This is under, this is over, but that is under. So for the green, let's analyze this one. This is under, this is over. So let's do the last one, and we'll do it in a different color. We'll do it this light purple. So I'm going to go from 2 to 3, go to the middle, hit the curve, go over to the right, and then go over to the left. And the purple kind of does, it looks like perhaps an underestimate. Okay, so if we add up the sum of all those areas, what are we going to get? So why don't you look at that for a second, think of what numbers you need to figure out, and then we'll work at that together. So in this function, we do not really, let me see, do I have a function? No, I don't. So I'm going to approximate my heights. So let's assume that the red has a height of 4.8. So if I'm going to figure out my area, so let's see if we can do area. So area is going to equal, what's the height, the midpoint height? It looks like it's about 4.8, and then my width is 1. So far I have 1 times 4.8 for my first rectangle plus second rectangle. It looks like the height is about 1 point, let's see, what's the height? It looks like about 1.5. My base is 1, so 1 times the 1.5-ish, 1.5 will be our second rectangle. Then look at the third rectangle. So that height looks about 1, maybe 1.2. So let's say 1.2. So I have 1 plus 1.2, and we're going to add up all those numbers and get the approximate area onto the curve using the Riemann sum method with 3 equal subdivisions. So when I add those areas up, so I'm adding 4.8 plus 1.5 plus 1.2, I'm getting 7.5 square units as my approximation. Okay, think about that, and we're going to move on to the next page. Okay, on this page, I pretty much summarized it all for you. So Riemann sums is an approximation of the area of a curve under a curve by dividing it into multiple simple shapes. We have used rectangles. You can also use trapezoids, but this is a rectangular method of estimating the area under the curve. So in the left Riemann sum, we approximate the area using rectangles of equal width, where the height of each rectangle is equal to the value of the function at the left endpoint of its base. Okay, right Riemann sum, you're going to draw your rectangles from the right height. Okay, then there's a third method called the midpoint method. So let's do that on the next page. Okay, the third method was, as I mentioned, the midpoint Riemann sums, and the height of each rectangle is equal to the value of the function at the midpoint of its base. Remember, you get the base by changing x divided by the number of equal subdivisions you wish to have. Okay, so that's a summary of the Riemann sums. Let's look at our problems next. Okay, so what we're going to do is we're going to do some practice with Riemann sums. So I'm going to leave most of this for you to do since I've shown you some examples. So for problems 5 to 10, we're going to use the Riemann sum to approximate the area under the graph of f of x on a given interval with selected points as specified. So let me give you some hints for 5. So we're going to look at 5. Whoops, so sorry. Let me go back. We're going to look at 5 down here. So first off, we have your basic parabola. So that looks pretty much like that. Excuse me. We're going to run it from 1 to 3, and they want us to have 4 equal areas. So 3 minus 1 is 2 divided by 4 is 1/2. So that means each of the areas will be 1/2 in length. So that means that if this is 2, that this will be 1.5. Excuse me, this will be 2.5, and the first problem calls for the midpoints. Okay, so try to do this work, and for 5, I am getting an area of 8.62. See if you get that area. Let's go on to the next page. Okay, problem 6, 7, 8, 9, and 10 are listed right here. I have rounded all my answers to the nearest hundredth. See if you can get them, and we'll discuss them next time in class. This is the end of this video.